Okay, it's Tuesday, and we're going to do some more review problems. Here's one from the 2008 Physics 212 second exam. Here we've got a long glass tube. It has a vibrating piston at one end and is closed at the other as shown. You fill the tube with sulfur hexafluoride gas, and very finely ground particles of quark are sprinkled in the bottom of the tube. The speaker is set to emit a sound at 400 Hz, and as the speaker emits its sound, you discover that quark particles collect in small, regularly spaced piles along the bottom, like shown in the picture. From the information given in the diagram, what is the speed of sound in sulfur hexafluoride gas? The tube is 67.5 centimeters long and is 4 centimeters tall. Okay, so number one, this is a standing wave problem, just like the flame tube and the surgical tube was in class. And probably the first thing we should do is try drawing a picture. First thing to notice is that there's piles of sawdust on the bottom. Remember that sound waves are longitudinal waves and they move back and forth. In this particular standing wave, places where the quark collects are places where the air is not moving back and forth. That's nodes. The places in between are antinodes, and that's where the air is sweeping back and forth really fast, so any quark that was on the bottom of the tube would be swept to one side or the other. So that means all the places where quark is are nodes, and the places in between are antinodes. So now we want to draw in the standing wave. Let's see how good I can do this. So where the antinodes are, quark gets swept off the bottom. Where the nodes are, the quark does not get swept off. And at this far left-hand side, where the piston is sweeping back and forth itself, that must also be an antinode. And so that means that we get a standing wave that looks something like this. Okay, well, drawings don't have to be great to still be useful. So in this case, when I count that, there are 1, 2 1/4 wavelengths. So there's 2 1/4 wavelengths of sound waves trapped in the standing wave in this length of pipe. So let's remember that the speed of sound is equal to the wavelength times the frequency. Notice in this case we're given the frequency and we're asked to solve for the velocity. So this means that lambda is going to equal v over f. We're going to plug that lambda into our original equation. I'm going to turn that 2 1/4 to 9/4. Hope you're okay with that. And we get 9/4 velocity over frequency equals the length of the tube. Our job is to find the velocity, and that's going to end up equaling 4FL over 9, which is going to equal 4 times 400 Hertz. Let's draw Hertz as 1 over seconds, times 67.5 meters, all divided by 9. Let's punch that into a calculator real quickly. So we have 4 times 400 times 67.5 divided by 9. And I end up getting 12,000, let me think about that for a second, that might be kind of fast, meters per second. If you don't mind, oh sorry, I'm going to just try typing that in again real quick. So that was 1,600 times, I see what it is, 67.5 centimeters divided by 9. And so this is actually centimeters per second, which if we get rid of 2 zeros, that brings us to 120 meters per second. Therefore, the speed of sound in this denser gas is actually a little bit slower. And when I think about it, that gives us a good answer. And hey, that's the answer to the question. Hope that one was fun. Let's try another one in a few minutes.